All right, let's get into it. Today, we're pulling back the curtain on how your computer really thinks. We're talking about assembly, the native language of your processor, the code that sits right on the metal.
So, you might write some beautiful code in Python or C++, but have you ever really stopped and thought about what happens next? How does that elegant logic you've written actually get understood and executed by the silicon in your machine? That is the big question we're tackling today.
And the answer, of course, is assembly. Now, it's not the raw ones and zeros of machine code, but it is the closest a human being can comfortably get to it. You really should think of it as the ultimate bridge that connects the software we all create to the physical hardware that makes it all run.
So, to kick things off, we're going to dig into what assembly actually is, and more importantly, why understanding it is such a powerful skill to have in your back pocket.
Here's what's so cool about it. Once you know how to read assembly, any program, and I mean any compiled program, basically becomes open source to you. Think about that. For cybersecurity folks or malware analysts, this is everything. It means you can take some malicious piece of code, reverse engineer it, and see exactly what it's designed to do.
But before we can write in assembly, we have to understand the CPU's own little world. We need to know where it keeps its tools and where it does all its work. So let's take a look inside the CPU's private workspace.
First up, we have registers. Imagine these as tiny, ridiculously fast little storage spots that are built directly into the processor chip itself. The absolute best way to think about them is like a workbench. When the CPU needs to do some math, it grabs the numbers it needs and puts them right there on its workbench for instant access.
And the thing is, not all registers are created equal. They have specialized jobs. In the x86 architecture, for example, the EAX register is where a function typically stores its final answer, its return value. ECX is our go-to for counting loops. And then you have ESP and EBP, which act like little bookmarks for a crucial area of memory called the stack.
So what is this stack? Well, it's just a special chunk of your computer's RAM. And the most important thing to know about it is its last in, first out rule. It works just like a stack of plates. You put a new plate on top, and you can only take a plate off the top. The CPU uses this as a kind of short-term storage closet to keep track of data and addresses while it's working.
So let's just quickly compare the two. Registers are right there on the CPU chip. They are lightning fast, but there's very little space. It's just a workbench, right? The stack, on the other hand, lives in your main memory. It's still fast, but it's a bit of a longer trip for the CPU to get there. The trade-off is that it's a much bigger space for temporary storage. These two are always working together.
Okay, so now we know the places where the action happens, the registers in the stack. Now it's time to learn the actions themselves, the actual commands that make the CPU get to work.
Now, assembly instructions can look a little weird at first, but they have a really simple grammar. Let's take move EAX 5. The move part is the instruction, the verb. It just means move. EAX is the destination, where we're putting the data, and 5 is the source, the data itself. You know, in a high-level language, this is just EAX equals 5. It's that simple. And once you get that basic structure, you've got a whole vocabulary of actions. You have add and sub for basic math. You have push to put some data onto that stack of plates we talked about, and pop to take it back off. Mul for multiplication. These are the fundamental building blocks for, well, everything. All right, now for what I think is the most fascinating part. How do we take these super simple commands and use them to build complex logic? You know, how does a computer actually make a decision or repeat a task over and over again?
It feels like it should be complicated, but the secret to every single decision a computer makes is actually incredibly simple. It all boils down to just two steps. First, you compare two values, and then second, you jump to a different set of instructions if the comparison is true. That's it. Compare, and then jump.
Let's walk through building an if statement. First, you use the CMP instruction, which compares two numbers. It doesn't store the result. Instead, it just sets these tiny internal flags inside the CPU that say, hey, these were equal or the first one was bigger. Then you use a conditional jump instruction, like JGE, which means jump if greater or equal. If those flags show the condition is true, the program literally jumps to a new section of code, skipping everything in between. And boom, that's your if statement.
Now, creating loops is just as elegant. While you could build one with compare and jump, there's often a special loop instruction to make it easy. This one command does two things automatically. First, it subtracts 1 from our trusty ECX counter register, and then, if ECX isn't 0 yet, it jumps right back to the beginning of the loop.
So imagine you want to do something 5 times. It's as simple as this. You start by moving the number 5 into that ECX register. Then you kick off your loop. On each pass, the loop command will automatically count down for you. 4, 3, 2, 1. And as soon as it hits 0, the loop is over, and the program just moves on to the next thing. It's like a built-in countdown timer for your code.
Okay, so we've covered the key building blocks, registers, the stack, and the basic commands for logic and loops. But let's zoom back out for a second and ask the really big question here.
And it's a totally fair question. I mean, with incredible languages like Python and Rust out there, why on earth would anyone bother with something so low-level today? Is this whole thing just an academic exercise?
No way. Knowing assembly is still a superpower. For malware analysts, it's non-negotiable. And high-performance computing, we're talking cutting-edge games or massive scientific simulations, you can use assembly to hand-tune critical pieces of code for every last drop of speed. For embedded systems, like the tiny computer in your thermostat, it lets you write super efficient code. And maybe most importantly, it gives you a true, deep understanding of how a computer actually works.
But look, in the end, watching this is just the first step. The source material for this whole explainer ends on a perfect note, really. True understanding only comes from doing. So if any of this has sparked your curiosity, the real journey begins when you open up an editor and start trying it yourself. Because without practice, you can do nothing.